Okay, this is the second part of the problem solving session of this week. And in the second part, we will talk about logarithmic differentiation together with the implicit differentiation. Okay, for the logarithmic differentiation, I want to start with a recall first, as I usually do. So we know how to deal with this derivative, right? A is a real number, it is a power, and if we want to take the derivative of this expression, we will just take the power down and then we will subtract 1 from the power. Then, since the base depends on x, according to the chain rule, you also need to multiply with the derivative of the insider function, which is f prime of x, of course. Okay. What if we change the roles of f of x and the power a? Let's change the roles now. Do we know how to deal with this derivative? We just covered that in the first lecture. This is the general exponential function and its derivation, it has its own derivation rule. It goes like itself times ln a, and since it is a composition of functions like powered is not just x, but f of x, you also need to multiply by the derivative of the power. So you should notice the difference between these two. This is a power function, while this is not. This is the second expression is a general exponential function, which has its own derivation rule like that. Okay, now I want to make the situation much more complicated by also putting x-dependent functions on the base and also on the power. What I mean is, what if we have both x-dependent functions on the base and on the power, and we want to take the derivative of it? How do we take this derivative? For this form, neither the first rule nor the second rule is applied, okay? For example, you cannot take this derivative by just taking the function g of x to downstairs and then by subtracting 1 from it. No, this doesn't make any sense. This is nonsense. It's completely wrong. Instead, we will learn a new rule, which we call as the logarithmic differentiation. Logarithmic differentiation. Okay, what is that? We use it to take the derivative. We use logarithmic differentiation to take the derivatives of functions of this form. For example, look at this one. X to the power x. Both base and the power depends on x, right? So this is a very nice example on which we need to apply logarithmic differentiation. So the question is, we want to find y prime. To find it, obviously we will use logarithmic differentiation. Okay, let's use it. I explained how to use it in my lecture videos, but here, let me remind it to you. You start by taking, this is the first step, you start by taking ln of both sides, okay? After putting ln's to both sides, then you are allowed to take this power down. You know, this is the useful property of ln function. You can take this power to here, to downstairs. Then let's see what happens. Then you will have an equation like that. And this is now a simple function to deal with while taking derivative, right? We don't have powers anymore, x-dependent powers anymore. It is now on the downstairs. So let's take the x derivative of both sides after this step. So first of all, here for the left-hand side, the most outer function is ln. So you will take the derivative of it first. So it goes like 1 over y times, you know, y is a function depending on x. That's why you will also multiply with the derivative of the insider function, y prime. And on the right side, you have a product. That's why you will apply the product rule, okay? Derivative of x is 1 times ln x plus x times derivative of ln x, which is 1 over x. You see you have a simplification here. That's why y prime from this line can be solved as ln x plus 1, and you need to send this coefficient to the right-hand side as times y. Look at what y was. Y was given as x to the power x. So this is a complete expression for the y prime where this coefficient comes from this 1 over y on the left side. It is moved to the right-hand side as a multiple like that. Okay, so this is a new tool for us. We call it as the logarithmic differentiation, and it is applied when your function to differentiate has both x dependent things on the base and also on the power, like that. And there are two steps in applying logarithmic differentiation. First, put ln to both sides and take this power down. And then second step is take the derivative of both sides with respect to x and do your computation. Okay, let's move on if no questions on that. I think this is a very useful recall for you, summarizing lots of things. Okay, so let's move on. You see again, ln x to the power ln x. We can quickly handle this question. This is very similar to the previous one. So I am using logarithmic differentiation. Logarithmic differentiation. So I am using it in this way. I am taking ln of both sides like that. And then I will be allowed to put this power down. So what I have is ln x. This is this red ln x like this. Also, let's change the color for this one. Okay, after this step, I am ready to take the derivative because it is easy now. It is not complicated anymore. This is 1 over y prime. And here I have a product. I will apply product rule. Derivative of the first function is 1 over x times the second, plus first stays the same times the derivative of this second expression. The most outer function is ln. That's why I am applying derivation rule for ln x. It is 1 over whatever you see inside, times the derivative of this insider part, which is 1 over x. Okay, from this line, you can easily solve for y prime as y times y was given like that. This is y times this whole expression, okay? It is 1 over x times ln x. You have a simplification here, plus, I guess, just 1 over x, where this coefficient comes from y on the left. Okay, another application of logarithmic differentiation is like this. Now, look at this one. I think before this example, I want to show you a more simpler example of implicit differentiation. Okay, this example will be about implicit differentiation. Okay, let's recall when do we apply implicit differentiation and what does it mean? Consider this equation, please. I have a question. Okay, this equation is given. We don't know an explicit formula for y, but still we want to find the first derivative of y function here. Even if, okay, my first question, is it possible to find an explicit formula for y from this equation? Can you solve for it for y? The answer is no. You see, you cannot decompose left-hand side so that you can solve for y in a suitable, convenient way. So let me write this warning here. We cannot find an explicit equation, explicit expression, let's say, not equation, but expression for y from this equation. We don't know it. It is not possible to find the explicit formula for it. But still, we can find the derivative of it. This is still possible. How? By using in such situations, so if this is the situation to find y prime, we will use implicit differentiation, okay? Okay, how do we use it? Let me show you. So implicit differentiation means that you take your implicit equation. By the way, if y cannot be solved explicitly, those equations are called implicit equation. This function defines implicitly your function, in other words. So then you start taking derivative of both sides with respect to x. And you should keep this in mind that y is a function depending on x. Don't forget that. So that's why the first expression is a product. So we will apply product rule to find the derivative of this first part. Product rule, how it is applied? Derivative of the first expression times the second, plus first stays the same, times the derivative of the second expression. You see, this comes from the derivative of the first part. Plus, what is the derivative of the second part then? Power comes down, you subtract 1 from the power, and since y is a function of x, since it depends on x, I will also multiply with the derivative of the insider function, so y prime. And then on the right side, we will just have, what is the derivative of 2? It is just 0, as it is a constant. So this is derivated as this one. You see, now I obtain an equation which consists of y prime, and I can easily solve for y prime from this equation. So here I see y prime, here I see y prime, and you can easily rearrange the terms. So y prime parentheses, 3y squared, okay, like that. And then I will solve it. So let's send this y to the right-hand side as minus y. So y prime is solved as minus y over x plus 3y squared. So this is your answer. And let's try to understand the core of this example. Our equation is given implicitly, where we cannot find an explicit formula for the function y, but still we can find the first derivative of it. How? By using implicit differentiation. If your equation is implicit, you will directly start taking derivative of both sides, okay? And while taking the derivative, you should keep in mind that y is a function of x. Then you won't do any mistakes while taking the derivative for the left side, and then you will just solve for your y prime function. This is what we call as implicit differentiation, okay? If no questions now, we are ready to solve the next example, which is much more complicated than this one. This was a previous exam question. Okay, so an equation is given, quite interesting equation, and we want to solve for the first derivative of y function. First of all, which tool should be used here? Look at the structure. Both the base and the power depends on x. That's why we will start with applying logarithmic differentiation, okay? Logarithmic differentiation. Why I am applying this? Because both base and the power depends on x. So I will take ln of both sides. This is what logarithmic differentiation means. Y to the power x. And then I am allowed to take these powers down. So we have y and ln. So we have these two equations. Now now it is not difficult anymore to deal with the derivative of this line because the powers come down already. After this step, I am applying implicit differentiation now, okay? So we will apply implicit differentiation for this line to take the derivative of it because the function y cannot be solved explicitly from this equation. It is an implicit equation. Take the derivative of both sides with respect to x. This is a product, we will apply product rule. So it goes like Derivative of the first expression times the second plus first times the first expression stays the same times the derivative of the second. Similarly, derivative of x is 1 times ln y plus x stays the same, 1 over y times y prime. You see, 1 over y times the derivative of the insider function. Okay, so for the left and right hand side, I take the derivative with respect to x. And the next line would be rearranging the terms to solve this equation with respect to y prime. Okay, let's do that. So I will collect all the terms, including y prime, to the left. ln x, and here I will have minus x over y, and I will send all the other terms to the right. ln y is already there, and this will be moved to right like that. And then, yeah, this is the expression for y prime, like this. So first we apply logarithmic differentiation, by taking ln of both sides, and then the rest is handled by applying implicit differentiation. Is everything okay? So far, so good?
Yes, teacher.
Thank you for the reply. And let's move on. There are more interesting questions for you today. Okay, look at this function. Even if it is not in this form x to the power x, or like f of x to the power g of x in more general, even if it is not in that form, I put logarithmic differentiation as a hint here. So let me explain why we should also apply logarithmic differentiation to this form too. Keep this in mind that logarithmic differentiation is applied to such forms where you have both x-dependent function on your base and on your power. This is for sure. Then you need to apply logarithmic differentiation to find the derivative. But for also the functions which are very loaded, like which contains lots of compositions like this one, using logarithmic differentiation will simplify the computation for you. What I mean is, of course, you can start taking derivative for this function, like taking the power down and then writing this whole thing inside and subtracting 1 from the power. And then you should keep multiplying the derivative of insider part. But this will take too long because look at the insider part. It is a quotient first of all. You need to apply quotient rule. While applying quotient rule, look at the numerator and denominator. They contain lots of products. For example, to take the denominator, you will apply twice product rule. Also for once for the denominator, the product rule you should apply. So lots of time. This is time consuming, too long. Instead of doing it like this, okay, this is also possible. You can start taking derivative directly like this. But as we noticed that it is very long, it should take too much time. It will take too much time. Instead, you will apply logarithmic differentiation. And you will understand why this helps to simplify things in a second. Let me apply it. Applying logarithmic differentiation means putting ln in front of both sides, right? ln of this whole thing. x plus 1, x minus 2 divided by x squared plus 1, 2x plus 3. And instead of writing cube root, I want to write it as a power. Which power I should put here? Which power I should put here instead of writing cube root?
1/3.
1 over 3, you're right. Okay, like that. And now I'm allowed to use every useful property of ln function. So this power can move down, can be moved down. ln And this part, okay, let me write it quickly and we will use another property of ln then. X squared plus 1, 2x plus 3. Okay, what do you remember about writing ln of a ratio? Let me recall you. Where is it? Yes.
Subtraction.
Yes, you can distribute ln to quotients like this by putting minus and to products like this by putting plus. Okay, let's use them in our example. So ln y is in fact 1/3 times ln nominator, I am writing nominator, ln of this thing minus ln of the denominator, of course. Like that. Okay. X squared plus 1, 2x plus 3. And then you can also distribute ln's to products. I have 2 products here, 1 product here. So let's write them as sums. ln y is 1/3 ln x plus 1 plus ln x minus 1. And also here, ln x squared plus 1 plus ln 2x plus 3. Like this. You see, this, okay, let me zoom out a bit. This very complicated form turns out to be like this one when we start by applying ln to both sides. Now, what is my aim? My aim is to find the first derivative of it. And now I am ready to derivate both sides. You see, I have just this line, and these are very simple functions to take the derivative. So derivative of the right-hand side is 1/y times y prime. 1/3 is just a coefficient there. Now I will take the derivative of these ln's, which are very quick and which are very simple to derivate. Derivative of ln x is 1/x. 1/x plus 1, 1/x minus 2 minus 1/x squared plus 1. And for this one, you should be a bit more careful because you need to multiply with the derivative of the insider part. Multiply with 2x minus, this minus applies here. It is 1/2x plus 3 times, similarly, derivative of the insider part is 2. And finally, the last line, our aim was to solve for y prime. By the way, these are the derivatives of the corresponding ln's. So y prime is this whole thing multiplied by y, right? And y function was cube root of something. Okay, let me write it. Cube root of ln x, x plus 1, x minus 2. I am writing y now, the given function y at the beginning. This divided by x squared plus 1, 2x plus 3. This whole thing, this big thing is just y, which comes from the left-hand side to the right-hand side as a product. And then I will write this, of course. And that's it. This is the first derivative of the given complicated expression. Okay? So sometimes it makes sense to apply logarithmic differentiation even if your form is not like x to the power x form. But if your function is too loaded, like too complicated, consisting of too much compositions, logarithmic differentiation helps, as you can see. Any question? Okay, let me move on. Next example is this one. It is a short one, but a very nice one, I think. So we want to find dy over dx. So we will apply implicit differentiation here. Without solving y from this equation, you can find its first derivative. How? By taking x derivative directly of both sides. Okay, how do you take the derivative of ln function? It is 1/whatever you see inside times the derivative of the insider function. And what is the derivative of 1? The derivatives of constant numbers are 0. Okay, let's handle this part. How do you take the derivative of this quotient? Maybe I should remind you the quotient rule here. F over G is derivated as F prime G minus Fg prime divided by G squared. So that's what we should apply here. It goes like derivative of X is 1 times the denominator minus X stays the same times the derivative of the denominator divided by the square of the denominator, okay? So this is 1 over X over Y is Y over X. So this is 0. I want to solve for Y prime. If this product is 0, what do you understand? As Y depends on X, it is not a 0 function, then this denominator should be 0, right? So this should be 0 then. And from here, Y prime is solved as Y over X. And this is the final answer. Okay? We solved for Y prime. So I want to move on if no questions. I will leave this example as an exercise for you. Please try it by yourself. And also this one. Let me see. Okay, let's solve this one together. Sometimes they give us such tables and then want us to use the values from these tables for computing some derivatives. Let me show you one of them. So the question is, find derivatives with respect to X of the following combinations. Okay, let's see. Let's choose one of them. Let's choose G and handle it. F is composed with this function, and we want to find the derivative of this expression at this given point, X equals 0. This is the question, okay? So let's start applying chain rule for taking the derivative of this expression. Sorry. F of X plus GH, I want to take the derivative of it, okay? The most outer function is F, so I will start by taking the derivative of the most outer function, so F prime. According to chain rule, I don't touch insider part. I write it as it is. And then I need to multiply with the derivative of this insider part, right? I need to multiply it with the derivative of this inside part like that. I am applying chain rule here. Okay, so what is this derivative then? What we have is F prime of this thing multiplied by 1 plus derivative of X is 1, G is G prime. Okay, like that. Now, to find the result of the derivative at the point X equals 2, I will insert at X equals 0, I am inserting X equals 0 everywhere. F prime of 0 plus G of 0 times 1 plus G prime of 0. Now it is time to look at the diagram table. We need G of 0 and G prime of 0. G of 0 is 1 and G prime of 0 is 1 over 3, right? Okay, let's insert them. G of 0 is 1 and G prime, this should be G prime of 0. As you can see here, G prime of 0 is given in the table as 1/3. So what we have done, we have F prime of 1 times 1 plus 1/3, 4 over 3. What is F prime of 1? Go back to table again. F prime of 1 is minus 1/3. Minus 1/3, 4 over 3. So the result is minus 4 over 9. Okay? So like this. We can also try to handle F. Let's try it. Okay, F. X to the power 11. What was the question? F of X to the power minus 2. I want to take the derivative of this thing and find the result for x equals 2. This is the question, okay? Similarly, apply chain rule, please. The most outer function is taking this minus 2 power. So minus 2 comes down. I don't touch the insider parts, okay? Then I subtract 1 from the power. You see, I handled the power while taking the derivative. The most outer function is handled. Then I need to multiply this expression with the derivative of this insider part. What is the derivative of that thing? That means, yeah, okay. So it goes like then 11x to the power 10. This is the derivative of the first expression plus f prime of x, of course. So this is the derivative of it. And then I will insert x equals 0 everywhere. So it goes like minus 2, 0 plus f of 0 to the power minus 3 times, I think, just f prime 0. What is f of 0 and what is f prime of 0? We need them. F of 0 is 1, f prime 0 is 5. So let's insert them. This is 1 and this is 5. So the result is, what is it? Minus 2 times 1 to the power minus 3 times 5. So this is, I guess, minus 10. Okay. Any questions? Any comments? Okay, let's move on. This example we will cover. An equation is given. Y function is defined implicitly through this equation. X cubed plus y cubed is 16. Then this time we want to find the second order derivative. Okay, this is the same as writing y double prime. These are different notation. We want to compute second order derivative y double prime at this given point. There is also an indicated point here. Okay, we will obviously use implicit differentiation for this one twice because y double prime we need. Okay, let's start taking derivative of both sides. 3x squared is the derivative of the first expression, 3y squared times y prime. And this is the derivative of this second expression equals obviously 0 because derivative of constants are 0. And next, what we should do to obtain y double prime, we need to apply implicit differentiation once more. So d over dx, again, I take the derivative with respect to x of both sides. Derivative of 3x squared is 6x. Okay, 6x plus. For the second expression, you need to be careful because this is a product function and that's why we need to apply product rule. So I'm applying product rule here, okay? Derivative of the first expression times the second stays the same, plus first stays the same times the derivative of the second expression. You see, I take one more derivative of it, equals 0. Is this part clear? Because this is an important part. This is a product function, both depending on x. That's why I'm applying product rule here. Derivative of 3y squared is 6y times the second function, plus 3y squared stays the same times the derivative of second expression. So y prime becomes y double prime if I take derivative once more. Okay, now we are ready to insert the point, right? Now I will insert the given particular point, x equals to y equals to. But look at your expression. Okay, we have x, y, they are handled as 2, 2, but we also have y prime. What is y prime for x equals 2 and y equals 2? Do we know it? Look at your first line. If at this line you insert x equals 2 and y equals 2, you can solve for y prime, right? So 12 plus 12 y prime is 0, so y prime is solved as -1. And then you will use this information here. Y prime is -1. So insert all this data to this line to solve for y prime as, let me insert all of them. 6 times 2, y prime is -1. 3 times 4, y double prime equals 0, of course. So from this line, y double prime is solved as -2 at the given point. Okay? So we applied implicit differentiation twice to find y double prime at the given point. Any questions? Okay, then let me move on. I will solve 2 more examples which are more geometrical, then I will stop. Look at this one. Let me start with the recall for this one. Okay, we are dealing with a parabola here. How do you draw the graph of such a parabola? Normally, we know how to graph y equals x squared. If you move it, for example, 1 units up, if this point is 1, then it is the graph of y equals x squared plus 1. You can also move it down. Let's say this point is -2, then it is x squared minus 2. So this is the usual shifting, the shifting of graphs, right? That's why for this, I want to visualize the question. I want to draw a picture. So let's assume that this is the graph of y equals x squared plus c, right? And what we want to find. The parabola is to be tangent to line, find c. So there is an arbitrary constant c here, and we want to find a number c, such that our parabola, I want to draw a tangent line. Okay, is tangent to this line, y equals x line at some point. We don't know at which point it is tangent. Let's call this point as A. Okay, so to make this happen, what should be this number c? The question is like that. First of all, tell me, okay, this is the equation of the tangent line, right? By looking at this equation, this is the tangent line. Can you tell me the slope of this tangent line? What is the slope of it? Look at the coefficients of x. So, you know, if a line has this equation, the coefficient of x gives you the slope of that line. So what is the slope of this line? Tell me the coefficient of x, please. It is 1.
1.
Thank you. So the slope of this tangent line is 1. And on thinking from a different perspective, we can also compute the slope by using the original function, right? What was the relation? The slope of the tangent line is also the first derivative of the original function evaluated at this point A, right? So it is in fact, also, it is also given as the first derivative of the function evaluated at that point A. So what is the first derivative here? It is just 2x evaluated at A. So 2a, and from this equality, we easily solve for a. The tangency point should be 1/2 to satisfy this slope information. Okay, so we solved that a is 1/2. This is y equals x line. That's why the image of it should be also 1/2. X and y components should be the same. You see, I obtain a point on the curve now, 1/2, 1/2. This point is on the curve. And now this information is so crucial because by using this point, I can solve for this arbitrary constant c. It should satisfy the equation of your curve, right? Okay, let me write. This point is on the curve, so it should satisfy the equation of your curve. I will insert y equals 1/2, x equals 1/2. So from this equation, you can easily solve for c as 1/4. Okay, that's the result. Any comments, any questions? So,
No.
question on the chat box, 2a. Where does 2a come from? F of x, the equation of your original parabola to which we draw this tangent line. So its equation is x squared plus c, right? And if you take the derivative of this function, it is just 2x. So evaluated at a, it is 2a then. That's fine. Okay, let's move on. Let me show you one more question before we stop. Okay, our last question will be this one. Okay, let's try to understand. The question is there anything special about the tangent lines to this curve and this curve? So two curves are given and their graphs are also given in the picture. So first curve is the blue one. Okay, it has a cusp at the origin. So this is the equation of the first curve as indicated here. And the second curve is the pink one. Let me use red for it. And its equation is also given here. It is the ellipse. Blue one is this blue curve. Okay, the question is about the tangent lines of them. So let's try to find some information about the tangent lines drawn at this point 1, 1. Let me draw a tangent line to the blue one at this point. You see, this is the tangent line to the blue curve. I want to find the slope of it now. What is the slope of this tangent line? How can I find it? Of course, I will go to the equation of the original curve. I will try to compute the first derivative of it at the indicated point. This is the slope. So the slope is in fact y prime evaluated at this point, 1, 1. This will give us the slope, okay? So, and the equation for the curve is given implicitly. Let's use implicit differentiation to find y prime here. Take the derivative of both sides with respect to x. So I take the power down and then I need to multiply with the derivative of the insider part, and the right-hand side is derivated like this. And then you need to insert the given point, x equals 1 and y equals 1, to find the value of the slope of the tangent line drawn to your curve at this point. If you insert this, y prime is solved as, at the given point, the first derivative is evaluated as 3/2, okay? This is the slope of the tangent line. Let's call this slope as m1. We will do the same for the second one. Okay, second curve is an ellipse, this pink ellipse. Now, at the point 1, 1, I will draw a tangent line to that ellipse. This red one is the tangent line to ellipse at the point 1, 1. Now, I am interested in the slope of this tangent line. What is it? Similarly, it will come from the first derivative of this equation evaluated at the indicated point. Okay, so just the equation is changing. The idea is the same. We will compute the first derivative of y to find the slope. Okay, let's take the derivative of both sides again to obtain y prime. How do you take the derivative? So 4x is the derivative of the first expression plus 6y times y prime is the derivative of the second expression, and derivative of 5 is just 0. Okay, and now time to insert the indicated point where x is 1 and y is also 1. If you insert this information, you will solve first derivative at the indicated point 1, 1 as -2/3. Okay, let's call this as m2. And remember the question. The question was, what is special about these tangent lines? And compare this m1 and m2, please. What is their product?
It's reflection.
Sorry?
It's a reflection.
So reflection, what do you mean by reflection? I think I misunderstood you. So if we multiply these two slopes, what happens? What is it? It is
-1.
-1, and the product of the slopes are -1. What does this tell you about the tangent lines? So they have product as -1. If the products of the slopes is -1, then the tangent lines are
Perpendicular.
exactly, tangent lines are perpendicular, okay? So this is the information. If you have product equals -1, then the tangent lines should be perpendicular. Now I can safely put this 90 degrees to my picture. Okay, let me also put them here. The line 1 with slope M1 was like that in the figure, and the second tangent line to ellipse with the red one with the slope M2 was like that. And since their products are -1, we understand that they are in fact perpendicular. Okay, that's the desired result. What is special about the tangent lines? In fact, they are perpendicular. How do we know it? Because we computed the slopes and their products are -1. If the slopes are equal, what happens then? If M1 is the same as M2, then the lines are parallel like this. If M1 times M2 is -1, then the lines should be perpendicular like that. By the way, for the last thing, let me also remind you how do we write the equation of the tangent line. For example, by using this slope information, let's create the equation of this tangent line. Even if it is not desired in the statement, but just for reminding you, it goes like y minus y0 slope times x minus x0, right? So y minus, this is your y0 and x0 points, y minus 1, slope is 2/3, x minus x0. So this will be the equation of the first tangent line. And for the second one, you can also create equation of tangent line. It will be like, just the slope is different. Y minus y0, slope is this time -2/3 times x minus x0, which is 1. These are the equations of tangent. You don't need to write them to understand. They are in fact perpendicular. You will just look at the slopes of them. If the product of the slopes are -1, they will in fact perpendicular. They will be perpendicular. Any comments on this solution? Okay, then I stop sharing my screen. I stop